Good morning friends. Now we have viscous flow in module number 2 fluid kinematics of the subject fluid mechanics. Okay. The question is show that for viscous flow through a circular pipe the ratio of maximum velocity is to the average velocity is 2. That is the maximum velocity to average velocity ratio is 2. So now we have a fluid element, that is the flow is happening in a pipe of radius capital R. We are taking a small fluid element of the fluid flowing in the pipe. The fluid element is having the radius small r. The length of the fluid element is delta x, and the frictional force is acting against the motion, that is to the left. So flow is to the right, friction is to the left. So we are having shear stress distribution and velocity distribution. At the center of the pipe, the velocity is maximum, whereas at the pipe wall, the velocity is 0. So that's why velocity distribution starts from 0, reaches maximum value at the axis of the pipe and becomes 0 on the other end, that is the bottom edge of the pipe. Whereas the stress is 0 because the flow is uniform at the center, so stress is 0 at the pipe wall. So my velocity is 0 but my stress is maximum. So 0 stress at the center of the pipe, uniform flow, whereas 0 velocity at the pipe wall but the stress is maximum. So we have already derived uh, velocity distribution equation. So u is equal to minus of 1 by 4 mu del p by del x dou p by dou x of capital R square minus small r square. So that is the velocity u is varying with the square of the radius r. So the velocity distribution across the section of the pipe is parabolic. We have the power of 2 in the equation. So we say that the velocity distribution is parabolic. So that's why the velocity distribution curve is shown as parabolic. Now we are deriving the expressions to show that the ratio of maximum velocity to average velocity ratio is 2. That is to prove this, we take maximum velocity equation to be found out. So we have maximum velocity at the center of the pipe. So that is when radius is 0. That is when we take exactly at the center of the pipe, velocity is maximum. So r value, small r value is 0 at the center of the pipe. So r is 0, that is neutral axis of the pipe, velocity is maximum. So we have the equation u max is minus 1 by 4 mu, that is we are taking u as u max 1 by 4 mu del p by del x. So small r is 0, so we have only capital R square in the equation. So we have only capital R square in the equation. So the discharge Q, that is across the section, is obtained by considering the flow through a circular ring of radius smaller. That is we are taking this smaller fluid element. So that is having the radius smaller. So here we are taking a circular ring of radius smaller, and the thickness of the circular ring is dr. So we are obtaining the expression for discharge through the circular ring, and we integrate it so that we are getting the discharge in the entire pipe. So we know that discharge Q is the product of area into velocity. Area of the element is 2 pi r dr, and velocity at the radius r is given as u. So area of the element is 2 pi r dr, and velocity is u. So flow per second, that is discharge q, is the product of area into velocity. Now we have, so 1 minus of 1 by 4 mu of del p by del x into, so that is my velocity is this 1 by 4 mu of del p by del x of capital R square minus small r square, and my area is 2 pi r into dr. So velocity into area. So that is dq. To obtain the full discharge in the entire pipe, we are having the integration from 0 to capital R dq. So integrating the expression from 0 to capital R. So we are integrating the expression with respect to R. So we have now, so taking the constants outside, so 1 by 4 mu of minus the dou p by dou x into 2 pi, we have only R, that is the radius inside the integration. So integration of this constant r square and integrating this smaller, we have r square by 2. Integration of r square into r, that is integrating r cube, is r to the power of 4 by 4. Having the integration limit 0 to capital R. So we have reduced the equation, this, simplifying the equation. So we have pi of pi divided by 8 mu of minus del p by del x into r to the power of 4. So we have average velocity u bar as q by area, because q is the product of area into velocity. So velocity is q by area. We have the expression for q. So that is pi by 8 mu of minus del p by del x r to the power of 4. Area is pi r square. We have simplified equation for u bar. Now we have the ratio of maximum velocity to average velocity. We know the equation for maximum velocity and we know the equation for average velocity. Everything will get cancelled. So we left out with 8 by 4. So the ratio is 2. So we proved that the ratio of maximum velocity to average velocity is 2. Thank you, friends.